Let's get started. I think we're expecting more people that'll come in as we get started. Welcome everybody to our another Sinter online quarterly meeting. We have an interesting agenda today. We're trying a few different formats with these meetings. So we're going to be starting with the science presentation and then getting some overviews of some recent books that came out that we think will be of interest to the SNO community. So we'll get right into the introduction. So I'm really happy to introduce Kehan Yang, who will be presenting this morning. She is a PhD candidate coming to us from the geography department at the University of Colorado Boulder. She's also affiliated with the Institute of Arctic and Alpine Research there. And her PhD research, which we'll hear more about, is focused on quantifying snow water resources in the Sierra Nevadas. She did her master's at the Institute of Remote Sensing and Digital Earth at the Chinese Academy of Sciences, where she also worked on monitoring alpine lake storage using satellite data. So let's take it away. Kehan, you should be able to grab the screen. Maybe before you start, I was going to just say to everybody, thanks for joining on a different time. We're experimenting with time shifting these meetings to try and accommodate people on different continents and time zones. So I know it's early for those of you on the West Coast of North America, but thanks for accommodating that. So, okay, Kehan, you should be able to grab the screen. You can take it away, and I'll give you maybe a time warning after about 20 or 25 minutes. You might still be on mute.
Can you hear me okay?
Yes, now it's very clear. Yeah, great. So take it away. Thanks, Kehan. Thanks a lot.
Thank you. Thank you very much for that introduction, Chris. Thank you all for having me today, and it is a great honor and a pleasure for me to present my work here. Today, I am going to be talking about bias correction of snow water equivalent using machine learning techniques in the Sierra Nevada, California. So I have selected 4 pictures here that I think will represent my research topic. The first one is the Lake Tahoe surrounded by mountains covered by snow, showing a very nice view of mountain snowpack. And the second one is a snow pillow site, which provides real-time ground snow observations. And the third one is the MODIS Terra satellite, providing the snow observations from space. And the last one is an aircraft or airborne snow observatory. And the ASO data is intensively used in my research, and I will go into more details later. So as we all know that seasonal snowpack is a very important water resources. Mountain snowpack is seen as a natural reservoir that stores water in the winter and gradually release water during the spring and the summer when water demand of human and ecosystem is at its peak. So more than 1 billion people relies on the seasonal snowpack and glacier-derived runoff as their primary water resources. However, this natural reservoir, which is often measured as snow water equivalent, is unevenly distributed in time and space. So in the Western United States, more than 70% of the annual runoff came from snowmelt, and snowmelt water strongly influences the timing and magnitude of streamflow. A lot of mountain regions have observed declined peak snow accumulation. We can see that these regions this as shown in this left figure, most of the stations has declined April 1st week. Because of the climate warming, precipitation has shifted from snowfall to rainfall, so that the snow accumulation has decreased and snow melt has shifted earlier in spring over many mountainous regions, which may result in higher frequency of natural hazards such as the flood and caused by rain on snow event and drought and the forest wildfires. So an accurate snow estimation, more specifically the snow water equivalent in real time, is particularly important to effectively facilitate water management and water supply forecasting, as well as to help with natural hazard early warning systems in the Western United States. So my research is focused on using statistical learning techniques to improve existing real-time SWE estimation. And my study area is in the Sierra Nevada, as shown in this right figure. So California is the most populated state in the United States with the largest economic and agricultural production. Snowmelt water from the Sierra Nevada, like this region, provides a main water supply for California. So there are abundant snow data sets available in the Sierra Nevada, so including the in-situ and the remotely sensed observations, a lot of ASO3 flights, and also some large-scale 3D estimations from reconstruction models and 3D data simulations. The question is how to combine all these data sets and get a more accurate 3D data in real time. So here shows a brief summary of ASO3 just in case some of you may be not familiar with it. So the ASO aircraft carries a LiDAR sensor to guide snow depths by subtracting snow on and snow off ground elevations, which has a very high accuracy. So snow depth is then multiplied by the snow density to get 3D data. So because the snow density has much less spatial variability compared with snow depths, even though the modeled snow density may have a lower accuracy, the final 3D data performs very well over large basins. So here shows an example of the ASO3 in the Sturm River Basin. And in this, it is intensively used as the ground truth 3 information in this work. So built on previous work, statistically based data fusion system has been designed for real-time 3D estimation over the Sierra. It uses a very simple linear regression model, LRM, more specifically the generalized linear model to model the impacts of independent variables on the dependent variables, which is the graded snow pillow 3 observations. We used a gap field real-time 3 F-scale data to scale the point 3 observations from snow pillow to grid cell at 500 meter spatial resolution. So that the 3 values can be better represent 3 at grid cell scale. So the F-scale data is derived from multi-satellite, and this data is available in near real time on Snow Today website as listed here, operated by Carl Riediger. The model is trained over the snow pillow sites and then applied over the mountain region. We can run LRM every day in real time. So in the Sierra Nevada, topographic information usually have significant impacts on 3 distributions. So here we also include 18 topographic variables to LRM, which is similar as those used in the PRISM precipitation data. Also, because 3 is often informed from like snow cover depression curves, we also introduce the daily mean F-scale as additional predictor variable to on 3 estimation. So for the historical 3 input, because the physical based 3 models like 3 reconstruction or 3D simulation are more accurate, usually is more accurate than the simple statistical models. We also have this historical 3 as an additional predictor variables for the LRM. So the question here would be like, we have a lot of reconstruction data available in the Sierra, but which data we want to use for the LRM? So, okay. So we compared 2 promising 3 estimation models, 3 reconstruction and 3 data simulation. 3 reconstruction as shown in this left panel estimates 3 backward from snow disappearance to peak 3 accumulation based on the snow melt rate. These 2 very simple, this primary equation shows here. So 3 reconstruction models largely outperforms the forward 3 estimation model because it does not include the precipitation data, which is a dominant variable for snow accumulation, but often contains very high uncertainty on the mountains. And the snow data assimilation as shown in this right panel relies on a satellite observed F-scale observations to update prior 3 states. in our Bayes framework. So the prior SWE estimates is derived from land surface model, and then it is updated by the F-scar observations. So both of these two models show high accuracy in SWE estimation, but one limitation of both of them is they cannot use it to estimate SWE in real time. So we compared some three data sets in the SIRA. So there are three physically based historical SWE data available, including two reconstructed SWE and RAC-int. So this is an early version SWE reconstruction. We used INT to represent the initial. So it is produced by Guang et al. In 2013. And the second one is RAC-Parble. It is an updated version of SWE reconstruction produced by Bear et al. In 2018, and the one SWE reanalysis, the SWE RAC-DA based on data assimilation. So this data is produced by Maguras et al. In 2018. So we compared all these three data sets and evaluated the performance of the SWE in over the snow core sites and this ASO in the Tuolumne Basin. So in the evaluation with the snow cores from 2003 to 2014 during their overlay period, there are almost like 2,000 staging years. So we can see that the RAC-DA generally has showed the best performance. So the bottom panel here shows the comparison between the snow cores and the snow SWE from the data set. So generally the RAC-DA shows the best performance. It has R-squared values of 0.92, which means it explained 92% of the variance in the snow cores SWE with MAEs, that is mean absolute error of 88 millimeter, and followed by the RAC-Parble, the updated version of SWE reconstruction. And then the RAC-int has the lowest performance, and also this we have the same conclusion when it compared with the ASO data in the Tuolumne Basin. Here shows the box plot of the evaluation result, R-squared and MAE. Also, RAC-DA shows the best performance with very high R-squared value and relatively low MAE. So based on this finding, we selected the RAC-DA as a historical SWE variable for the LRM. So then we ran our model daily from 2000 to 2019, and then we did an evaluation to compare the SWE in the snowfield sites. Again, on the target day, then compared it, we also included the snow dust and the national water model SWE in the comparison to see how does it perform in compared with other two operational data sets. So here shows the scatter plot. We can see that generally LRM shows a relatively higher R-squared value compared with snow dust and national water model SWE. It has explained 84 variation in the snow cores observations. It is a little bit lower than the SWE reconstructions as we shown before here, but it is much higher than the other like the snow dust and the national water models. We can see that all of these three data sets has a negative bias compared with the snow cores data. So also in the evaluation with ASO data, we see that we can get the same conclusion that LRM is more accurate than other two operational SWE data sets. The box plot here shows the R-square of LRM is significantly higher than snow dust and the national water model SWE. And also like the p-bias of the LRM is the absolute value of the p-bias is much lower than the snow dust and national water model SWE. So based on this evaluation results, we also find that the LRM is has a relatively it has consistently lower p-bias compared with ASO data. So our next step is to see whether we can use ASO data to further improve LRM3. So here shows an video uh, that showing the LRM bias compared with ASO data in the Tuolumne Basin. So we can clearly observe that there are some consistent patterns over time. So like for these low elevation valley regions, the model generally has a very blue color represents that the model has an overestimation over these regions. But for the high elevation regions like this here, the model generally, like most of the times, it has underestimation, sorry. So red color represent underestimation for these regions. So based on like this finding, so we also compared it with like the elevations. So for example, if we compare three residuals with elevations, it shows a significant positive relationship between them two. And some of these patterns is also related to the land cover classifications. We can see there are some similar patterns between these two images. So based on this finding, we further like designed a bias correction framework to post-process LRM3. So we assume that the three residuals are consistent related to some variables, as we see that it has a positive relationship with elevation, and it is also related to some topograph like the land cover classifications. So we assume that we can model the three residuals and as well as extend the model in time. So similarly, we created a framework as shown in here to represent this progress. We have developed, we have the dependent variable, which is the three residuals over the Tuolumne River Basin, and independent variables, which are topography data, daily topograph data, daily mean FSCA, and the land LRM3. And also we have included another canopy density as an additional independent variables in the model. So we choose a couple of statistical models in the training of the three residuals from very simple linear scaling Gaussian process regression. These are very simple linear regression model to more sophisticated like neural network, SVM, and random forest gradient boosting machine. So from simple to more sophisticated models. These models are easily accessed in the R package CRAD. So we tried all these models to train the three residuals in the Tuolumne Basin. And we have assumed that the model can be applied or extend in the time. And how can we prove that? We listed some steps. So firstly, we used similar as a leave-out evaluation to prove if that the model can be extended over time, which means if we don't have the ASO data, but we want to improve the three accuracy, we are trying to use the three residual models built in a previous day to correct the three on the target day. So so step one is firstly, we need to remove ASO3 data on and after the target simulation year, just like to mimic we are in a real-time situation. We don't have the ASO data that is after or on the same year. Step two is select a historical ASO3 and LRM3 to calculate the residuals. Basically, we need to find a historical ASO data set shows similar patterns. Then we assume these similar patterns will consistent on the target date. Then this model trained on that historical data can be applied to the day we want to do the bias correction. The step 3 is model residuals using the selected methods. The selected methods mean these statistical methods like simple or very sophisticated models. And step 4 is applies models on the target date and get LRMPP3. PP means post-processing. So we train the model and get the LRM post-processing suite after bias correction. Step 5 is to evaluate, to look at if this LRMPP3 using the ASO3 removed in the step 1, just because we ran all this simulation in a historical period. We have this ASO data for the entire period. So we can use that to evaluate if this bias correction frame work or not. And the last step is compare LRMPP3 with SnowPillow3 to determine the best statistical model. Basically, what we will do is for the Torah basin, we got this LRMPP with all different six statistical models. Then we use the snow pillow observations in the Torah basin on the target day to determine which statistical model we want to use at the final result. So let's look at how does this work. So here shows like the leave one out evaluation. Basically, so the red color represents LRM original model, and each dot represent one simulation day. So the ASO data is available from 2013 to 2000, to present. So we use this leave one out evaluation start from 2014. Only use, for example, if we want to model or to do bias correction for 2014, the first day we will choose ASO historical data from 2013. Then here shows the R-squared values and the Bayesian-wide p-bias. The evaluation is conducted by comparing the posted by LRMPP with the ASO data set removed at the beginning. So generally, we got this table with the summarized which summarized all the results. So LRM has R-squared value of 0.770. It is kind of lower than our last evaluation results because we used different days, and here include a lot of very low 3 years, like 2015 with very low 3 data. And it has a high negative bias of 0.27, and the absolute p-bias is 33%. LS means linear scaling. So I order all the statistical methods from simple to more sophisticated. So we can see that R-squared actually increases between from simple statistical models to more sophisticated machine learning algorithms like random forest and the gradient boosting machine. These two are all based on the tree-based machine learning algorithms. So it actually has shown very similar results. If we did picked some days to look at the results in more details. So as we see that in 2015, April 2015, these are all very low 3 days. And our original LRM has a quite low R-squared values because as it is a statistical model, it relies heavily on the ground three observations, no-pillar observations. If there are a lot of zero values or over a lot of regions, the model generally doesn't work. And if we use the model, it will get a very bad or worse performance. So the R-squared value on this low 3 days are very low. And the bias correction have shown generally a good performance to increase the R-squared values and also increase the increase the sweet values to reduce the p-bias. And also if we look at these later years with more historical ASO data can be used in the bias correction, we can see that the patterns are more consistent. So if I picked three, like two, like one 2 days, one high sweet day, one low sweet day, just for example, to look at the spatial patterns of the three. So as we look at these R-squared values, we can conclude that the bias correction has improved the spatial variation of the three compared with ASO data, while LRM generally has shown a little bit lower spatial correlation with ASO data. But if we look at the spatial maps, like at this scale, it is quite hard to identify which model has the best performance. Generally, they did some similar things. And for some like simple models, it may have less power to correct the spatial variation, but for it has improved that it has increased the sweet values for these regions compared with LRM. And if we look at low sweet day, so the first column is this ASO, we can see there's a distinct sweet gradient from low to high elevations over this ASO data. But for LRM, generally it has a very high underestimation with like lighter blue colors. And these bias correction models is trying to increase these sweet values for these regions, but more like for the rainforest and the GBM, these two, and the BRM, and actually they all show similar results, but it increases the model performance. So the next step, so the last step actually is compare LRMP post-processing three with no pure three to determine the best statistical model, which means we only use one model in the final post-processing. So it can be either one of the 6 statistical models used in the training. So generally, when we compare the LRM original with LRM PP, the R-squared value increased by 16% and the p-bias reduced by 52%. It is an improvement, but if we look at the p-bias here, even though it has shown a little bit higher or less negative bias, but still it has a high range of the p-bias, like Bayesian wide p-bias. And if we look at closely to the state I selected before, for the 2015, this year's R-squared, it is selected models that increases R-squared a lot, and also pose the three values to positive bias to a more less negative bias, but like this day, it is select models that has shown quite high positive bias. But for the later years, as I said before, with more ASO data included in the bias correction, the model shows more robust performance.
Can you wrap up in the next 2 or 3 minutes, Kehan?
Yes.
Oh,
so
look at that. Perfect time. Okay,
okay.
Sorry.
To conclude, so in this study, actually, we developed a statistics-based linear regression model, which combines ground observations, remotely sensed data, and physically based Sierra analysis to estimate Sierra in real time for the Sierra Nevada, California. The LRM3 explains 84% variance in the snow course over the Sierra Nevada with a -8 Bayesian-wide p-bias and 85 variance in the ASO3 over the Tuolumne Basin with a -9% p-bias, both suggesting high accuracy than the other two operational 3 data sets in the comparison. And the bias correction framework suggests significant improvements with 16% higher R-squared and 53% lower p-bias. compared with original LRM3. However, the robustness of this model needs further improvement. Lastly, we find that all bias correction methods ranging from simple linear scaling to rather sophisticated machine learning algorithms effectively improves the accuracy in the Turing river basin. But no single algorithm performs consistently better than others. So future works will be focused on applying this bias correction framework to a large Sierra Nevada ranges, try to extend the model in space and also to improve the robustness of this model. So at the end, I want to acknowledge my collaborators, Dr. Carl Whittaker, Dr. Steve McGrath, Dr. Thomas Payne, and his ASO team to provide data and suggestions, and also my advisors, Dr. Noah March and Dr. Keith Musselman support for this research, and my funding source from NASA's Water Resources team. Thank you all for your attention today, and thanks again for this presentation opportunity, and I will take any questions.
Great. Thanks a lot, Kehan. Excellent overview of your work. I invite people to enter questions into the chat, even as questions come to you during our subsequent part of the talk. We're going to, I think, keep moving on the program just because we have some other presentations to get to. But thanks a lot, Kehan. That was a great overview. And again, people, put your questions in the chat. Kehan's email is there. And please feel free to reach out to her. Kehan, there's already one question for you in the chat box, so please feel free to take a look at that as we go on. Okay, we're going to stay in the Sierra Nevadas and just change the focus a little bit. So Jeff, I'm going to ask you if you can share your screen and come online. We're going to these Sinter meetings always have a slightly different format from session to session, and today there are 2 new books that have come out that are of interest, I think, to the SNO community, and we've asked the authors of those books, who are respected elder members. I use the term elder with the most respect here for Jeff and Matthew. So Jeff, please come on, and there we are. I can see you now, and you should be able to share your screen, and please give us the overview of your book. Please take it away.
Okay, do you see my screen?
Yeah, I can see your screen. I'll come on in about 10 minutes and give you a hand wave, but please take it away.
Okay, so it turns out that a good way to clean off your desk is to write a book. John Milak and I have been working together since we were both at Santa Barbara, really starting, and in the mid-'80s, we started these projects. And basically, for me, the water molecule is about as complicated as I can deal with, and John worries about what goes with the water molecule when the snow melt. So our co-authors are Steve Sadro and Jim Sickman, and they were both students when they started this work with us. Jim is now a fairly senior faculty member at UC Riverside, and in fact plans to retire soon. Steve is an assistant professor at UC Davis. So essentially what this book has is kind of an amalgamation of a lot of the things that we've learned over these many decades of work. It appeared in early January from UC Press. I'm not very happy about the $80 price on this. As my son says, if it were $20, all his friends would buy a copy, but at $80, none of them will buy a copy. For those of you who are climbers, the cover photograph is from Vern Clevenger. Vern did some of the first 512s in the Yosemite and Tuolumne area. Let's see, I'm trying to make this advance now. Okay, so there are 12,000 lakes in the Sierra Nevada, but most of them are pretty small. And so there are you know, about between 3,000 and 4,000 lakes that are over 10 hectares in size. They're in general pretty clear, and the soils in the Sierra are pretty shallow. They're mostly granitic catchments. We get deep snow, and the isotope analyses seem to indicate that in a given year, about 90% of the water that comes out is from this year's snow. And the reason is there's not much groundwater. There's also not a lot of overland flow. So most of the runoff has, in fact, interacted with the rocks and the soil. This is an example of one of the well-studied watersheds in the Sierra. This is Emerald Lake in the Cahuilla River drainage. Picture on the left is what it typically looks like in the winter, and the picture on the right is what it looks like in the summer. You see not a lot of trees there to get in our way, and most of the runoff goes directly into the lake. One of the reasons we studied Emerald Lake is that there's a granitic sill at the outlet, and so there's for this reason, we think there's very little water leaving the watershed as groundwater. So the funding, it really started with the California Air Resources Board, who were interested in the possibility of acid rain in the Sierra, and a bunch of other funding agencies in that. On the right, I've listed the students who worked on this during, over the years. And as you can see, you probably recognize a lot of the names. And some of these people are now pretty prominent snow scientists. So the contents of the book, there's a lot about snow and watershed hydrology, and then with the biology people involved, there's work on watershed biochemistry and limnology, and there's a chapter at the end on what we might expect in the future. In terms of, are there temporal trends? There's large interannual variability. There's some episodic events, and I'll discuss one of those later. And those affect not only the amount of water, but the chemistry also. So in these areas, the hydrologic cycle, as you can guess, is dominated by snow. The most important characteristic of some of our graduate students was being able to handle a shovel. And you can see a pit that's over 6 meters deep on the left. And then on the right, some of the early work that was done on terrain and the effect of the distribution of snow really started with Kelly Elder. And of course, Kelly can ski really well. And so, we made this basin look like a pincushion in terms of the sampling that we did. The interannual variability, the wettest years are about 10 times as much water as the driest years. This is the chart on the right is an amalgamation of all the snow pillows in the Sierra above 2,300 meters or so, which is about 7,500 feet. You can see the wettest year on record was 1983, and basically it was wet because it just kept snowing. That the snow peaked in May. 2017 is the wettest year of this century. 2016 was sort of an average year, and then 2015 was the driest year on record. And you can see this huge difference between these years. We see the same sort of thing if we look at it spatially with remote sensing. This is some of Steve Margulis's work. Again, looking at these big differences between the dry years and the wet years. And emphasizing this is one of our MET stations at a little over 10,000 feet. The person climbing it is 6'3", and you can see on the right the same MET station in 2017. Okay, some of the trends, and some of the stuff has actually not really been published anywhere else except this book. One of the questions with snow, of course, is there's a lot of variation with elevation. And so the graph on the lower right looks at the snow courses that have over 70 years of data. And what we can see is that the ones where there's any sort of a statistically significant decrease in the April 1st snow water equivalent are all at the lower elevations. And there's only one snow course that has increasing snow water equivalent, and that's at pretty high elevation. But you can see that there are a lot of snow courses that are not, we're not seeing any sort of statistical significance. And so the statistics of analyzing this is one that one needs to be a little bit careful about. And then one of the things that Danny Marks showed in his thesis on this work back in the early 90s is that, you know, of course, we know that snowmelt is driven mainly by the net solar radiation, but and usually the net long wave is going to be negative because of the emissions at night. But what Danny showed, and what this graph shows pretty well, is that when the net radiation, that is the net solar plus the net long wave, when that crosses the zero line, that's really the time that when the spring melt kicks in. The snow has a lot of influence on the lakes themselves, and you can see that depending on how much snow there is, it's going to last longer. And then what you see in the graphs on the right is that particularly the graph on the lower right is that the temperature of the lake is really sensitive to the duration of the snow cover, and therefore to the amount of snow. So the lakes are going to be a lot warmer at the end of the summer in the situation where the snow disappeared earlier. You can see the same thing here. If you look at the graph at the top, this is just the time series of the maximum lake temperatures with the different colored dots or shaded dots based on the amount of snow. And then if you look at the graph on the lower right, that's the same set of data, except now the x-axis is the amount of snow rather than the year. And what you see is that, again, in the years where there's a lot of snow, the lakes remain much cooler. An interesting thing about this, and this is work that John and his colleagues did, what about nitrogen cycling in these basins? And what you see is that on the left graph, that the nitrate pulse is greater in the years when the snow lasts longer. And the reason for that is that there's processes that are going on under the snowpack that in fact produce nitrogen. And then of course, there's one outlier in this, and you can see the 1987 value. And that was when a pretty big thunderstorm actually hit the lake during August. And of course, uh, the snow comes in off during the winter, comes in off the Pacific, so it's pretty pure. But the summer thunderstorms, that air has boiled up out of the Central Valley, and therefore the nitrate concentrations in the rainfall are much greater than in the winter snowpack. And that what you can see, the graph on the right is that there's in the years in which there's the snow is later, there's less nitrogen retention by the watershed. Okay, and the sort of the typical trends we see. This is one of the things I like to emphasize to people. If we're worried about the effects of climate change on California and Western Nevada, probably the most important are those in the Sierra Nevada, both in terms of their effect on the water supply and their effect on fire. That is, the two biggest climate-related problems we have in California are water and fire. And so the Sierra is really the most important thing to see. Any long-term environmental change is going to be linked to this variability. What we see is there are slight increases in air temperature at the higher elevations, but we don't see much change yet in the snow. And there's not much of a warming trend in the lake temperatures because it's the interannual variability in the snow that drives most of that variability. And that is it. Buy the book and I'll buy you a drink when I see you.
Awesome. That's a great plug, Jeff, especially knowing the people that I know on this call. That's a good way to drive up your sales. Great overview, Jeff. Really appreciate it. Thanks a lot. Great looking book as well. So I think that's definitely of interest to the community. I'm going to move on to introduce Matthew Sturm. A lot of you know Matthew. We're going to move out of the Sierra Nevadas now, where Kehan and Jeff had us for the last 45 minutes or so. And Matthew is someone I've worked with in the Arctic. He focuses mostly on Arctic snow. So Matthew, I'll share my screen because I know I have a couple of visuals, and I'll let you take it away.
Yeah, thanks, Chris. And I'll just tell you to switch at some point. So, hey, thank you for having me on. The book I wrote, it's called A Field Guide to Snow. Let me take a few minutes just to talk about where it came from. I think about close to 20 years ago, I'll put it this way. I fancy myself, or at least I enjoy greatly, art. I do pen and ink and watercolors. And about 20 years ago, after working in Barrow for a very long time, I wrote a book called Apun, which is Inupiat for snow cover, Apun, the Arctic Snow. And it's a kid's book with pen and ink drawings. And it got used in a lot of schools. And so at some point I wrote a book called The Teacher's Guide to Apun. And the Teacher's Guide didn't get a lot of use except by a few teachers, but it was sort of the start to this book. It was a simple sort of explanation of snow cover, starting from snowflakes falling out of the sky and piling up on the ground and so on. And that had always sat there. It was published by UA Press, but it didn't really go anywhere. And I guess it'd been in the back of my mind that a book like that was needed. So the motivation for this book, for those who remember Ed LaChapelle's Field Guide to Snow Crystals, and of course, Ken Liebrick, who's a good colleague of mine, his Field Guide to Snowflakes or Snow Crystals. Anyway, those were two motivations. And so a few years ago, I started writing this book. I looked at the guest list here, and a lot of you I've brought up to the Arctic at times, and those of you who've been out with me know that once I get into a snow pit, it's hard to get me out of there. The guys I've traveled with always were impatient because I found myself doing this. Yeah, well, this, Chris, is about right, huh? It's a pretty thin snow pit compared to Jeff's 6 meters, but there's still plenty to look at there. And so I've always loved just getting down in the snow, and I've loved art. And I thought, well, let me try and write a book that helps lay people understand snow, from where it comes from in the sky to how it lands on the land, how it metamorphoses, and then what it means in terms of water, what it means in terms of climate, and what it means in terms of aesthetics. So that's what the book is about. Chris, do you have one other picture? I like this picture a lot. That's my son in the middle. After about 30 years of leading long snowmobile traverses, probably 30 or 40,000 kilometers, I finally got my son to go. That's Charlie Parr on the right. Charlie's my tech. We just put out a paper on drifts, and we had just finished about a 700-kilometer traverse, and it ended up Toolik Lake. I still love the snow, so I'm still getting out there. I think the best bet, one thing I'm happy about, Jeff, my book is cheaper than yours. It's in a sort of field guide format, so people can stuff it in their packs. It's on real durable paper. It costs, I think, $24, or there's e-versions. And I tried to put in there what I both know and love about snow. And probably the best bet is for those of you who get the book to let me know how it goes. I decided I teach a 600 level course that's basically snow cover and snow physics. And watching my students over the years, I think I'm going to use this as a kind of introductory text. So I think, unless you have any other pictures, Chris, that's really what I wanted to say. And I'm happy to answer questions about the book. And really, for this community, I'd love to get some feedback, whether it captures what people know and love. Oh, I see Mark there. Yeah, I think Mark's seen the book. So, and Chris has a copy. Probably better to ask my colleagues. There we go.
Yeah, I need a high resolution version. You just sent me the PDF. I need the real one.
Okay, you'll get the real one, Mark. I'm not as much of a drinker as Jeff, and I think I'd go broke. So, but the offer, Jeff's offer, still also is there for my book as well.
Fantastic. Thanks, Matthew. Yeah, so I can hold up. Sorry, Jeff, I don't have a version of yours to hold up alongside Matthew's, but yeah, thanks for the overview. Oh, there we go.
Great. Oh, there it is. Yeah.
Yeah, thanks, Jeff. So yeah, I think what we'll do now, so I'm really pleased that Matthew and Jeff joined us today to give an overview of their books. I'm really pleased that Kehan joined us today. I mean, the point of these meetings is to try and do something a little bit different. So not just science talks. So Jeff and Matthew did a good job there, but also to highlight some of the science that's being done by people at early career stages, and Kehan did a great job of capturing that today. So I think when we think about what we want to accomplish in the Sinter community, hopefully this is keeping people engaged and interested. We tried a different date and time today. We may go back to our Friday afternoon time slots. So stay tuned to emails from me. I'll keep people posted on that. I also want to highlight Yori Carter. He's on the call today. We had asked him to give a quick overview of the new, soon-to-be new Sinter website. We're tight on time, and I don't want to rush him into a position where he can't give an overview that's proper. So Yori's going to come back and do it on our next meeting. But he's a student at University of Washington who's been working really hard on updating the look and feel of the Sinter website. So thanks a lot to him, and he will be featured on one of our next meeting. So also just want to highlight that all of these quarterly meetings are recorded and archived and available through the Sinter website. So if you miss one, if you have colleagues who might be interested, please let them know. And there's more information, on Sinter on the website. So this takes us to the top of the hour. There's unanswered questions in the chat, mostly for Kehan on her presentation. So please take a look at that, Kehan, and respond to people as you can by email. And yeah, thanks a lot to everybody for joining today. Stay tuned. We do these every about 3 months or so, and so we'll keep the group posted. All right. So thanks a lot, everybody. Stay well, and we'll see you all soon. Thanks to Kehan, Jeff, and Matthew. Great to see everybody.